Warning! The video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. Don't let the name of this video fool you. We are solving basic differential equations, but we're still in Calc 1. We're still doing anti-differentiation. It's just that at this point, you can actually start solving basic differential equations. So I'm going to read this paragraph and then we're going to talk about it. I often call differential equations by the name Calculus 2.5, and this is because you don't really need third-year calculus at all to do differential equations. But it definitely requires first and second-year calculus. You're in first-year calculus right now, about to go into second-year calculus, hopefully. The basic idea behind a differential equation is that you've been handed an equation containing derivatives of an unknown function, and you must use that information to somehow recreate the original function. And by the way, if you've been watching my video series on antiderivatives, you know that the way I view differentiation is like a ladder. And you're at the rung that we would call the function f. And when you take a derivative, you step down a rung. And take another derivative, you step down another rung, and so on and so forth. And we now know that climbing the ladder is called the anti-differentiation process. So we are taking antiderivatives to climb the ladder. Right now, we only know the name of the next rung up. We don't know the name of two rungs up, but that's totally fine. Not that big of a deal. All right. So somebody comes in the room and they say, here's a function that, or here's an equation that involves the derivative of a function. Maybe they'd say it's this right here. Okay. And they say, what was the original function? We now know how to find that original function, sort of. We can just take its antiderivative and say the original function climbing that ladder would be add 1 to the power, divide by the new power, make sure you put a plus c on there, and that was some form of the original function. That is not the identical original function, likely, because we don't know what c is. They would have to give us some further information so that we can really nail down what that constant is. That constant will get its own name in the future. Now, this example I'm about to show you is actually not required for Calc 1 or Calc 2, but I like it, so I'm going to show you it. Suppose I told you that I have f prime is equal to 2x. Now, right now, if I said f prime is equal to 2x, you should be thinking, what would I take the derivative of to get to 2x? And you would say x squared. This is what you're looking at right now. It's called a slope field. And it's the slope field of 2x, which means that wherever we are, whatever x value I'm going to look at, the field is going to return the slope at that very moment. So for example, this point I'm dragging around is giving me the value of 2x as a slope. So for example, if I was at x equals 0, notice the slope of this little element here, we call this a lineal element, but the slope of this lineal element is a 0 when x is 0. When x is 1, the slope is 1. When x is 2, the slope is 2. When x is 3, 4, and so on and so forth. The further out I get, the steeper the slope gets. I hope you understand that. Okay, but this lineal element changes slopes depending on where the x value is, because again, this is a slope field for 2x. Now, if you were to watch this, you could see that it kind of carves out. If you were to slowly kind of graph out a line following these lineal patterns here, you could probably see that you're going to get parabolas, because again, the function, which is the antiderivative of 2x, is y equals x squared, and then plus some value of c. And that value of c, I'm just going to add a slider here, you'll be able to see that that value of c, notice it's lining up with this slope field very nicely, right? So this is, the slope field just gives us a visual of all of the derivatives at any given moment for the function we're dealing with. You can also do stuff like this. So let's suppose we go back here and let's say we want secant squared, because we know that the derivative of secant squared, or sorry, the antiderivative of secant squared is the tangent. Now that is a crazy looking mess, right? It's a total crazy looking mess. But let me zoom in here and really try to showcase this. Notice that x equals 0, the slope is probably about a 1. And then as I move over, the slope increases and it almost goes vertical. Now, if I were to graph y equals its antiderivative, which is tangent of x, you could see that now if I grab this lineal element, any time that I'm moving along this, the slope of the lineal element there matches the slope of the tangent line for this curve. It's a really cool visual. I dig it. It's not important for your Calc 1 or Calc 2 courses right now, but it's still really cool. Now, hopefully you're still with me. My lectures are not meant for those who are faint of heart or for those who believe that they just want to memorize some stuff and move on. It's for those who are really interested in learning. And so that's why I do that. Every once in a while, I'll throw something at you that's a little more theoretical than you probably need. That's okay. All right, hopping back into what we're doing, let's deal with a differential equation. This is a differential equation because you have a derivative of an unknown function equaling something. We do not know what f is, but we know what its second derivative is. Okay, well, if I know its second derivative, I could find the antiderivative of this second derivative. Now, the antiderivative is going to be obviously the first derivative. So again, we'll ask ourselves, what will we take the derivative of to arrive at that function? Well, we would take the derivative of f prime first of all. So f prime of x is equal to, we're going to have this 2/3 hanging here, and then we're going to have times x raised to the add 1 to that power, so raise the power by 1, so now it's x to the 5/3, and we're going to multiply the front end by the reciprocal of that new power. Then we're going to add a c, and when I do this, I add a c sub 1, just because I'm going to get a constant in the next step as well, so it's nice to label these as c sub 1s and c sub 2s. Clean this up a little bit, so that's going to be 2 over 5 x to the 5/3 plus c sub 1. And then we again ask ourselves, what would we take the derivative of to arrive at that function? Because we want what f is, not what f prime is, but we want to go up the ladder yet one more step. Well, going up the ladder one more step, f of x, which is the antiderivative of f prime, is going to equal, well, let's see, here's f prime right here. We're going to take the 2/5, so let me go ahead and write 2/5. We're going to multiply it by, let's see, I'm going to raise that x to the 5/3. I'm going to raise its power by 1, so now it's x to the 8/3. Notice I left room out front because I'm going to multiply the front end by the reciprocal of that new power, so by 3/8, plus the antiderivative of a constant is that constant times x. So it'll be c sub 1 times x. By the way, if you're wondering why I do those little brackets on my c's, it's because technically it's a capital C, so I'm just trying to showcase it's a capital. And then because we just took an antiderivative, there's going to be yet another constant. Every time you take an antiderivative, a constant pops out. So here we have yet another constant because we took 2 antiderivatives. Cleaning this up, 2 goes into 8 4 times, and so you get this. 3/20 x to the 8/3 plus c sub 1 x plus c sub 2. That is the original function. We don't know what c1 and c2 are, and that's a problem. We would love to know what those are, but you cannot, in this situation, find them. They have to give you what are called either initial values or boundary values for you to be able to find what c1 and c2 are. So let's see how that's done, because that is very, very powerful. So suppose that instead of just handing us the second derivative and saying, what's the function, they instead say, here's the second derivative, f double prime is equal to 2 plus the cosine of x. But then they give us a couple more pieces of information. For every piece of information, we'll be able to lock down one of those constants. Now, I shouldn't say that's always true because it's not always true, but in the cases that we're going to deal with for right now, that is going to be true. So let's go ahead and start with the fact that we've been given the second derivative. We're going to climb that ladder to get to the first derivative and climb it again to get to the original function f. So let's ask ourselves that ever-present question: what would you take the derivative of to arrive at that f double prime? Well, I would take the derivative of f prime, which is equal to, let's see, the antiderivative of 2 is 2x. And what would you take the derivative of to arrive at a regular old cosine? Well, that would be the sine. And then plus the constant that gets spit out from every antidifferentiation. And then, looking at this bad boy right here, we ask ourselves that ever important question: what would you take the derivative of to arrive at that function? Well, the function f is what I'd take the derivative of. All right. Well, let's see. What's the antiderivative of 2x? You'd add 1 to the power, so it'd become an x squared, and you would divide by 2. So those 2's would cancel, and you would just have x squared. Look how easy it is to check to make sure that's right. Take the derivative of x squared, you get to 2x. What would you take the derivative of to get to the sine? If you say the cosine, you're wrong. It's the negative cosine of x. Be very careful about that. And then plus, we would take the derivative of c1 times x to arrive at c1. So c sub 1 x. And we get yet another constant with this antidifferentiation. There we go. So now I could possibly find those constants identically by using this given boundary information right here. They're telling me that when I plug 0 into that function, I should get an output of -1. So let's use that information. So let f of x equal -1 and x equals 0. Let's see what happens. F of x is -1. Our x values are zeros. I'm just writing it in like I would for an algebra class just to showcase kind of what's going on. There's a lot that you're learning right now, so it's understandable. And this becomes a -1 is equal to a -1 plus c2, or in other words, c2 is 0. Great. So now we know our function looks like this. F of x is equal to x squared minus cosine of x plus c sub 1 x. Well, we've only used one of those initial conditions or boundary conditions. Let's go ahead and use this other one. F at pi over 2 should be 0. So I'll let the output be 0 and let the input be pi over 2 minus the cosine of pi over 2, which we know is going to be 0, plus c sub 1 times a pi over 2. Let's see, subtracting pi over 2 squared. Actually, we could probably square that. Well, I'll just subtract it from both sides. That's subtracting pi squared over 4 from both sides. You get negative. Cosine of pi over 2 is 0, so you get c sub 1 times pi over 2. Multiply both sides by 2, and divide both sides by pi. And sorry, my c sub 1 got jagged there. We get that c sub 1 is equal to a negative, let's see, pi over 2. Is that right? Multiply by 2, divide by pi. Yep. So we now know what our constant here is. We can now substitute that back into f of x and we'll be done. F of x is equal to x squared minus the cosine of x and then minus pi over 2 x. Perfect. And we have completed this problem. And now we arrive at one of my favorite problems of the semester. This is just a fun problem, and it's a great use of antidifferentiation. So, and it's also the last problem in this video. You're a crime scene investigator. Dun dun. That's the sound every CSI makes, I think. A car braked with constant deceleration of 16 feet per second squared. And that's a known fact about rubber and asphalt rubbing against one another. So there's a car skidding to a halt, right? And there's the rubber of the tires against the asphalt of the road have a friction coefficient that causes deceleration of 16 feet per second squared. I'm just saying that could be found, right? Then you're a crime scene investigator. You show up and you say, what kind of tires are those? And they tell you, and you look it up in a book and then you say, great, deceleration constant is negative 16 feet per second squared. And you measure out the skid marks that was left there, and they're 200 feet long before the car came to a complete stop. Okay, and it didn't hit a tree or anything like that, so it was just skid mark of 200 feet long, and that's it. How fast was the car traveling when the brakes were applied? You can actually solve that now. That's too darn cool. So let's list out the given information and list out what we want. I've read the problem. So that's the win. I've read the problem. I think I know what's going on, but drawing a picture is not going to help out here. But at least listing the given information and what we want might help out. So this is, by the way, when I'm saying stuff like that, I'm saying it so you know that the tactic to solve any word problem is always the same. Read it, then try to somehow understand it by listing the information out, drawing pictures, whatever you can. State the givens and the unknowns, or the desired things you want. And that's what I'm doing right now. The things we were given in terms of mathematics. A car braked with constant deceleration of 16 feet per second squared. So deceleration is acceleration with a negative sign. So we know that the acceleration is equal to a negative 16. Okay. Let's see. What else they hand us? Skid marks measure 200 feet. Okay. Actually, let me not use math yet. I'll say acceleration is equal to. And then let's say length of skid is equal to 200 feet. I think is what it was. Yeah. Before coming to a stop. How fast was the car traveling? So want speed or velocity of the car once brakes were applied, once skid starts. All right, that's the given information and what we want. Now we're going to transform that given information into mathematics. That's kind of important. That's very important. In fact, the want is probably the easier piece here. So we want velocity. V stands for velocity. And we want that, we'll just say at time 0. Because nobody cares about time that 5 minutes before this person arrived on the scene. What we want is immediately when they hit the brakes, what happens. So that'll be our time 0 value. So speed, we want that. Okay. And let's see, acceleration. Well, the acceleration, they tell us throughout the entire skid, from time 0 to time whenever the skid stops, is negative 16. So I'm going to say this implies acceleration for all of time as far as from beginning of skid to the end is a negative 16. And that's feet per second squared. It's kind of important because we want to make sure that all of our units match in this problem. The length of the skid, well, that's a distance, right? So if we assume that the position, and just to let you know, if you have not been my student for this entire semester, or if you haven't seen any of the speed, acceleration, and velocity problems I've done, and it's been a while, it probably has been, to be very honest with you, the 3 functions you need to be very aware of are position. S of t is equal to position. Position, that's how you spell that. And then the derivative of positions in terms of, let's say, feet. The derivative is feet per minute. And so that's going to be a velocity. Velocity. Again, if position is in feet, then this is feet divided by time, which we'll say per second, actually. Feet per second. And if you take another derivative, which means you're dividing by time yet again, the second derivative of position is the first derivative of velocity, which is the acceleration. And that is in feet, again, per second squared, because you're dividing by time again. Each derivative you're dividing by time. So the length of the skid is a position change, right? So we're going to assume that the position at time 0, we'll call that 0. And the position at time, well, we don't know how long it took for this car to eventually stop. So I'm going to call that time end. It's how long it took for, I have no idea how many seconds that is. So it takes so many seconds for it to finally stop. But by the time it does, it's gone 200 feet. And again, these are in feet, feet and feet. Just making sure all the units are the same. Given that information, we should be able to kind of build everything out. All right, so let's go ahead and start, and I'll kind of create a little bit better view of all this information right now. So let's make it a more robust thing. Let's tie up all the position information right now. So S of 0 is 0, and S at time end, whatever time that is 200. Another thing that we'd like to know is the velocity at time 0. We don't know that. But you know what you do know? The velocity at time end. How quick is the car moving by the time it stops? It's a trick question, everybody. 0. And finally, the acceleration throughout the entire movement is -16. Those are our given conditions. And we could start with the lowest rung on this ladder. Remember, I always think of it as a ladder, and you have some function, we'll call it S. Its derivative, S prime, is 1 rung down, and its second derivative is 2 rungs down. That's the acceleration. So if I happen to know the acceleration, its antiderivative would give me the velocity, and the antiderivative of the velocity would give me the position. So let's go ahead and start with the acceleration. If the acceleration is -16, that implies the velocity function is, well, the antiderivative of a -16 is a -16 t. Remember, the variable here is t. But we have to add a constant because of our antidifferentiation. Okay. And I could, by the way, start subbing in values, but I personally like to climb the full ladder off to the right-hand side here. I like to regenerate my position function completely. So let's take one more antiderivative. So this implies the next antiderivative, which is going to be the position function, should equal the antiderivative of t. So -16 times the antiderivative of t, which is t squared over 2. Okay. Plus the antiderivative of c sub 1, which is c sub 1 times t, plus the next constant because of our antidifferentiation. And I could clean that up, so I will. I'm going to write that as a -8 t squared plus c sub 1 t plus c sub 2. Now, keeping things clean, because I really do like to rewrite quite a bit just so that I can keep my paperwork clean. I don't need that ladder picture, so I'm going to erase that. And no idea what just happened there. I'll go ahead and do this. And what I'm going to do is go to my conditions, the things that they've given me. Each one that I use, and the conditions are right here, each one that I use, I'll cross out when I'm done with it. You can only use a condition once. So I know that the position at time 0, I'm calling 0. So let's go back over here and use that piece of information. So I'm told that the position at time 0 is 0. That means, so S of 0 equals 0 implies that 0 is equal to, if you let this left-hand side be 0, you'll get on the right-hand side all the t's 0, you'll get that c sub 2 must be 0. So c sub 2 is 0. Great. I'll go ahead and erase c sub 2, and I will cross out that condition I've used. The next thing I'm going to use is not the the position at time end, because that's not really, well, I guess I could. You know what? I could use that. Let's go ahead and do the position at time end. The position at time end is 200. So let's go ahead and write that in. Position at time end equals 200. Well, that will imply the output is 200 in my position function when the input is time end. Time end squared plus C1 time end. And you look at that and you think, well, that's not really helping me. And I would agree slightly, but there is actually something else we can do. We still have more information to go through. So I'll cross that out. This is not information because we can't use it. We don't know it. We've already used the acceleration. So the only other thing I need to use here is that velocity at time end is 0. That's the only other piece of information I have. I hope it's going to be helpful. So let's use that here. The velocity at time end, let me write it in blue. Velocity, oh, it was supposed to be blue, but it didn't quite work out. Velocity at time end, we know is 0 because the car is parked there. And so therefore we'll let the output for our velocity there be 0. We'll let the input be time end. So the input was, or right hand side was negative 16 time sub end plus C sub 1. And we've now used all the given information. Just doesn't seem fair. It's as if we're not going anywhere. It's like we don't have anything. But then you take a look at this group of information. You have two equations here, and you have two unknowns. Your unknowns are C1 and time end. That's a system of two equations and two unknowns. I can easily solve that. So let's go ahead and solve that system of equations. I will take the second equation, this guy right here, and I'll solve for C sub 1. C sub 1, we'll just say that's C sub 1, there we go, is equal to 16 times time end. And I'll take that 16 times time end, and I'll substitute that into this other equation right here. So this will imply that 200 is equal to negative 8 time end squared plus C sub 1, which is 16, time end times time end, which is time end squared. That is 200 is equal to 8 time end squared. Divide both sides by 8, you'll get 25 is equal to time end squared. Take the square root. Remember, time is the number of seconds it took for this car to stop, so it's not going to be plus or minus, it's just going to be the positive version, 5. It took 5 seconds for this car to come to a complete stop. That did not answer my original question, but once I get that, it took 5 seconds for the car to come to a complete stop, I can then go back up to this formula and say what C sub 1 is. C sub 1 is going to be 16 times time end, which is 80. And now I can find my velocity function. Remember, my velocity function all the way up here is negative 16t plus C1, and we found out that C1 is 80. So velocity at any given moment is negative 16t plus 80. Is that right? Negative 16t plus 80? Yeah. And so the question is, what was the velocity at time 0? The velocity at time 0 is 80. And remember, this is in feet per second. I'd like to transform that into miles per hour. So I'll just say multiply this. I know there are 5,280 feet per 1 mile. So that gets rid of the words feet. And I happen to know there are 3,600 seconds in 1 hour. So that will get rid of the word seconds, and I'll have miles per hour as my answer. And this roughly transforms to 54.5 miles per hour. Very, very good problem. Wonderful use of anti-differentiation, and shows you just with a little bit of information what you can derive. You don't need a ton of information to get stuff like this. All right, so I'm done with this video. In the next video, we'll do some synthesis problems, basically pulling together a bunch of stuff from the past.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.